determine the percent of H2O2 that decomposes in the time using the value of K to be that. Okay, so be smart about it. If you look at the value of K, the units are second negative. So second negative or time negative, just know that it's a first order reaction. Okay, now in this case this is decomposition, so decay is a first order reaction. So here you can also use the value of K to determine the rate of the reaction, the order of the reaction. So we are told that determine the percent that decomposes in the time using K is equal to that. So the time for the concentration to decompose is 600 seconds, and then also again for 50 seconds. So we've got two parts of the question. We have to determine the percent that decomposes in the time using that. Now if you look at the value, if you look at the integrated ratios, an integrated ratio is the only equation that combines the value of K, time, and the concentration. So it's a natural log of the final concentration being equal to negative KT plus the natural log of the initial concentration. Now if you're going to bring the final and the initial on both sides to become a minus. Now if you've done your logs, you know that when you're subtracting two logs with the same bases, you can combine the log and then divide the values. So you end up with A final over A initial being equal to negative KT. Now we want to do away with a natural log. So you can introduce the inverse, which is E, exponential on both sides, right? E. So you know that all these are going to be raised to the power E if you introduce the E, right? So you notice that where there's a natural log, it remains as it is. Since they are inverses, they'll just cancel out. And then on the right, since there is no natural log, it automatically becomes the power, negative KT. So this is another form of a first order reaction that can be useful in this kind of a question. F fine over A initial is equal to E to the power negative KT. So for the very first part, since we want to determine the percent, this is better in that this is already giving us a fraction or a ratio. So it's better off final in respect to what we started with. Okay? So all we just have to do is just substitute on the other side. So for the 600 seconds, the ratio of the final to the initial is obviously going to be equal to E to the power negative K. K was obviously 6.40 times 10 to the power negative 5, and then multiply by the time. The time there is 600 seconds. Don't forget you have second negative and second, so we are going to cancel out. So 600. So when you plug in those values, the value you're getting is 0.9629. Okay, so that's the value, that's the ratio of the final to the initial. So what does that mean? So you found the ratio of the final to the initial. So now in this case I want you to focus on the percentage. Okay, the percentage of what? The percentage that decomposes. If you look at the ratio of the final and the initial, let's say if you add 10 and then it decomposes to 4. Okay, or let me not say decomposes to 4. Let's say you're at 10 and then what remains after decomposition is a 4. It means this is your final, that is your initial. And what that means is you have got 4 over 10 final over the initial. This percentage is what has remained, not what has decomposed. So to find what has decomposed, first of all find the percentage of what has remained, and then you subtract from what was available initially. So in this case what we found is a ratio of what has remained in respect to what was there at start. So this is not what had decomposed, but this is what has remained. So we can express it in terms of a percentage by multiplying by 100. So multiply that value by 100 times 100. So it's like final over initial times 100, which gives us 96 0.29, which I can summarize to be 0.3%. This is how much had what remained, because it is final over the initial. Now to find how much had decomposed, you have to find the difference. So subtract from 100 how much had remained to determine how much had decomposed. So you end up with a value of the 3.71% to have decomposed in this case. Same concept can be applied to the different time of the 400 seconds. Okay, so you can find the ratio of the final to what had remained initially. So here you notice that the value is 0.9720, okay, times 100. To get a percentage, it becomes 97.2%. This is how much had remained. Equal, you can subtract from 100 to determine how much had decomposed. So you find that it's 2.8% in this case. So that's how you handle question 8. You are easily able to come up with the ratio of the final to the initial by expressing the equation in the form of an exponential using the natural log equation. That is for the first order integrated equation for the first order reaction.